Rates of change. Quantity versus rate. A quantity is an amount of something. So for example, I can have 10 books, or 13 feet, or 2 pounds, or 50 miles. As opposed to, a rate is a ratio of two different quantities. So for example, maybe I can read 10 books in 1 month, or I travel 13 feet every 2 seconds. Or I can lose 2 pounds every 1 week. Or my car travels 50 miles in 1 hour. Now we're going to analyze the relationship between position, velocity, and acceleration. The position of an object at time t is given by the function s of t, or sometimes x of t. Velocity is the rate of change, or the derivative, of the position function, meaning v of t is equal to s prime of t. So velocity is the slope of the tangent line on the position function, since slope of the tangent line is interchangeable with derivative. Acceleration is the rate of change, or derivative, of the velocity function. So acceleration is the derivative of velocity, v prime of t, which means it is the second derivative of the position function. So acceleration is the slope of the tangent line on the velocity function. And now we're going to take a look at what are some of the units in rates of change. A lot of times units can really save us and help us understand what's going on in a problem, what we've been given, what we're being asked for. So a position function like s of t or x of t have units that are a quantity. So some examples include distance, like miles, meters, etc. But it could also represent an area, so inches squared, a volume, feet cubed, or even something like money or people. So a position function, again, have units that are a quantity, an amount of something, and we're used to that amount of something being a distance in a lot of our examples. A velocity function, like v of t, or the derivative of any position function, must have units that express rates, that idea of a quantity over a time. So some examples include meters per second, dollars per hour, or feet squared per minute. And then acceleration functions like a of t, or the derivative of velocity function, is a rate of change of a rate of change. So the units that they have is a quantity over a time, or quantity over a time squared. So examples of these acceleration units look like feet per minute squared, or miles per hour squared. Now let's take a look at, well, what is speed? Sometimes people incorrectly interchange speed and velocity, but it's not exactly the same thing. Speed is actually the absolute value of velocity. Speed is the absolute value of velocity. So speed is always positive, whereas velocity takes into account direction. So furthermore, speed is actually a scalar or a numerical value, whereas velocity is a vector since it takes into account direction. In this class, we're mostly going to focus on rectilinear motion, which is movement of an object along a straight line. So we have two different possibilities. We can have horizontal linear motion, which is moving left or right. So it depends on the sign of velocity. If velocity is positive, then the object is moving right towards positive infinity. And if velocity is negative, then the object is moving left towards negative infinity. And if I have vertical linear motion, so I'm traveling up or down, if velocity is positive, then the object is moving up. And if velocity is negative, then the object is moving downward. In this example, we're going to suppose a robot moves back and forth along a line, and that the position of the robot in meters over time in seconds is given by the function s of t. So we have this position function over here given. And part A is asking us to draw a diagram to illustrate the motion of the robot. So let's come over here and just label the axes with units. So t is time, which we were told is in seconds, and s of t, the position, is given to us in meters. So any point on this particular function, so let's say if I look at the point 1, 1, that means at 1 second the position of my robot is at 1 meter. And I want to draw a diagram to illustrate the motion of the robot, which will be along a horizontal line. So the possible positions of the robot in meters, well, if I look across this graph, the range of this graph extends from -1 up to +3. So those are the units that I want to go ahead and label, or the tick marks I want to label on my horizontal line to draw this diagram. So I'm going to go ahead and put -1, 0, 1, 2, and 3, because remember, this is going to describe our location in meters. And we're going to go ahead and start with thinking about what's happening at time 0. So at time 0, my robot is at a location of 1. Now, to avoid sort of cluttering things up, instead of drawing a robot, I'm just going to use a dot to represent my robot. And that's where he starts at, so that's at time equals 0. So since this is one-dimensional here, I'm going to have to label the time on top of the location. So at time 0, the location of the robot is 1 meter. And the location of the robot stays fixed all the way until 2 seconds has passed. So from t equals 0 to t equals 2 seconds, the robot is in the exact same place. But at 3 seconds, the robot manages to get to 3 meters. So between 2 and 3 seconds, the robot is traveling to the right. So if I go ahead and sketch what's happening here, at time 3, my robot's going to be at 3 meters. So I'm going to go ahead and put t equals 3 and draw a little arrow to indicate the direction that the robot traveled. So notice the robot traveled to the right, and my slope, which would be my velocity, is positive. That's why I'm traveling to the right. Now from 3 to 4 seconds, I have that the robot is in the same location. So between 3 and 4 seconds, the robot is still at a location of 3 meters. So between t equals 3 and t equals 4 seconds, my robot just stays put. But then the slope of my position function between 4 and 6 is negative. And notice at time 6, I end up at a location of -1. So I'm going to be traveling to the left during the time interval from 4 seconds to 6 seconds, and I'm going to end up at a location of -1. So if I go back, I'm going to turn around, and I'm going to end up at a location of -1. So I'm headed to the left, and this is going to happen. I'm going to end up over here at t equals 6 seconds. And then finally, between 6 and 8 seconds, I start traveling to the right again. I have to end up by 8 seconds at 0. So I have to end up at a location of 0 meters. So I'm going to have to turn around, head back to 0, and I end up there at t equals 8 seconds. In part B, we want to graph the velocity function v of t on the xy plane provided. So here we have a position function. We just need to draw the derivative of this position function to come over here and get velocity. So we're going to have to analyze the slopes. So between 0 and 2 on the position function, I have a slope of 0. So I'm just going to go ahead and put a slope of 0 here. So that means between 0 and 2 on my velocity graph, I have to be at 0, which means on the x-axis. And at 2, I have a sharp corner, so I'm non-differentiable there, so I'm going to have to put an open circle at 2. Between 2 and 3, I have a linear function with slope 2, rise over run, so up 2 over 1. So I have a slope of 2 between 2 and 3. So between 2 and 3 here, I have to have a slope of 2. And again, I have open circles at 2 and 3 because I have sharp corners, I'm non-differentiable. Between 3 and 4, I have another horizontal line on position, so that slope is 0. So back to the velocity function over here, 3 and 4 is going to have to be back down on the x-axis. And then between 4 and 6, I have to figure out what this slope is. Well, I go down to right 1, so my slope is -2 between 4 and 6. So over here, between 4 and 6, I'm going to go ahead and draw my slope of -2. Again, open circles because I'm non-differentiable at corners. And the last interval I'm going to look at is between 6 and 8. So I have to identify the slope here. So the rise is 1 and the run is 2, so it's +1/2. So between 6 and 8, I have a slope of +1/2. So here I have the graph of the derivative function. So this is v of t, meaning the units, the time units are still in seconds, but the velocity units here are now meters per second. So what this tells us is that at time 1, the velocity is 0. The robot is essentially at a stop. So at time 2.5, the velocity is 2 meters per second. And since velocity is positive, that means my robot is traveling to the right, which we can match with our diagram in the previous part. For part C, find s prime of 2.5 and explain what this represents. We actually just talked about this. At 2.5, we identified that the slope of that piece is 2, and the slope of the line is the derivative, the velocity function. So s prime of 2.5 is equal to 2, and the units there would be meters per second, which also gives us our explanation. At t equals 2.5 seconds, the robot is traveling 2 meters per second to the right. For part D, find the robot's speed at t equals 5. So remember, speed is the absolute value of velocity. So what we're looking for is v of 5, but we want to make that value positive. So v of 5, remember, is s prime of 5. So the derivative, the slope of the tangent line. So that slope of the tangent line at 5, or the slope of that line, is -2. So that means that what we're really doing is taking the absolute value of -2, so we get +2. And again, the units are going to be meters per second. In part E, find the acceleration of the robot at t equals 5 seconds. So we know the velocity of the robot at 5 seconds is -2, and acceleration is the derivative of velocity. So here's what I know. I know that v of 5 is -2. We just identified that in part D. So the acceleration is its derivative. So a of 5 is v prime of 5. Well, the derivative of a constant, -2 is a constant, is 0. So we have 0 with the units of meters per second squared. So acceleration has a distance over a time squared. In part F, when is the robot standing still? We talked about that in the diagram. The robot was standing still between 0 and 2 seconds and between 3 and 4 seconds, which notice that's where velocity is equal to 0. So when is the robot standing still? So on time intervals, so I'm going to say time intervals between 0 and 2, and the other interval of time is from 3 to 4, and the units here are seconds. And in part G, finally, when is the robot moving to the right and when is the robot moving to the left? So a robot's moving to the right when velocity is positive, and we identified those intervals where velocity is positive. Between 2 and 3, velocity is 2. And between 6 and 8, velocity is 1/2. So we're looking at the time interval from 2 to 3 seconds and another time interval from 6 to 8 seconds. And I'm moving to the left, or my robot's moving to the left, when velocity is negative. So when the slope of the line on the position function is negative at between 4 and 6. So the time interval is between 4 and 6 seconds. Also take a second to notice all of our intervals were open intervals because of those places of non-differentiability. So we don't want to actually include those values. Now we want to understand the difference between distance and displacement. Distance is a quantity that measures the length of the entire path traveled, whereas displacement is the net change in position, or it's the straight line distance between the initial position and the final position. So let's look at an example with some horizontal linear motion. Let's suppose you take a straight path to school every day. So this is your starting location, and let's say there's a Starbucks, this is my Starbucks, that's 5 miles away on a straight path to school, and then at 15 miles away is school over here at Mount Sac. So if we wanted to talk about the total distance traveled, so let's go ahead and say here's where you started out and you traveled to Starbucks, then you went to Mount Sac, and then you had a really rough day so you needed another Starbucks. So here's where you're at. If I want to calculate the distance traveled, that's the length of the entire path. So that's adding up all 15 miles to get to Mount Sac and the 10 miles that you would have to travel to backtrack to the original Starbucks. So your total distance would be 25 miles. But your displacement, that's just the straight line between where you started and where you finished. So that would be only 5 miles, the displacement. So the relationship here is that distance is always going to be greater than or potentially equal to displacement. Let's now take a look at average speed, average velocity, and average acceleration. So average speed over a time interval is distance over time elapsed. So distance being the absolute value of the difference between the two positions over the change in time. Whereas average velocity is displacement over time elapsed. So we don't have the absolute value bars around the change in position, and then we have the change in time on the bottom. So graphically, average velocity is the slope of the secant line, because we're passing between 2 points here, 2 times correspond to 2 points, on the position graph. So notice we're on position, S of t1, S of t0. And average acceleration over a time interval is the two velocities at different times, t0 and t1 subtracted, over the change in time. So the average acceleration is the slope of the secant line again. We're still passing through 2 points, but this time we're on the velocity graph. So a lot of students tend to mix this up. If they're asked for average velocity, we have to know to use position. And if we're asked for average acceleration, we have to know that we're using velocity. And we also have the notion of speed increasing versus speed decreasing. So at a particular moment in time, an object has or is increasing speed or speeding up if both velocity and acceleration have the same sign at that time. So if both velocity and acceleration are both positive or both negative, then my object is increasing speed or speeding up. The way we are decreasing speed or slowing down would be if velocity and acceleration have opposite signs. So one has to be positive and the other one has to be negative. So if you kind of just think about driving, in order for us to be speeding up, our velocity is positive. That means we're going in a forward direction, remember? And our acceleration would have to be positive as well. So we'd have to be stepping on the gas and traveling in a forward direction if we're going to be speeding up. But if we're slowing down, we're traveling in a forward direction. Our velocity is positive, but we would need to press on the brake. That's deceleration. So that acceleration quantity would be negative. So they would be opposite for us to be slowing down. Now we have a big example. A particle moves according to the function s of t, a position function, which is this cubic polynomial here. And t is measured in seconds and s is measured in feet. Part A, find the velocity at time t. So here our job is to take the derivative of the position function. So v of t is equal to s prime of t, and we can apply the power rule over here to each term. So we have 3t squared minus 3t minus 18, and then just plus 0. Since we're talking about velocity here, the units would be a rate of feet per second. In part B, what is the velocity after 2 seconds? Now we're going to use our answer from part A and substitute 2 in for time. So v of 2 is equal to 3 times 2 squared minus 3 times 2 minus 18. So we end up with 12 minus 6 minus 18, or negative 12, again, feet per second. For part C, when is the particle at rest? Well, the particle is going to be at rest when velocity is equal to 0. So this phrase here, we want to think, when does v of t equal 0? So we're going to go ahead and set the derivative v of t, which we solved already, 3t squared minus 3t minus 18. We want to solve when is that equal to 0. Well, let's factor out the 3t squared minus t minus 6 equals 0. And then we'll factor the quadratic, so t minus 3, t plus 2 equals 0. So now we can set each factor involving t equal to 0, so we end up with t equals 3 and t equals negative 2. Now here, one of these two answers doesn't make sense, negative 2, because time is in seconds. So the particle is going to be at rest at 3 seconds. And now part D, when is the particle moving in the positive direction? So we said an object is moving in the positive direction when v of t is greater than 0, when velocity is positive. So we do know what the velocity function is. So the velocity function is 3t squared minus 3t minus 18. That's a quadratic function. So to determine where that quadratic is greater than 0, I would say the easiest way to do it would be to think about the graph, because we already factored and solved for its x-intercepts when we set the function equal to 0. So if I were to do a quick sketch of my velocity function here, it's going to be an upward-facing parabola with 0's x-intercepts at 3 and negative 2. And it's going to be a really rough sketch. I'm just going to go ahead and draw an upward-facing parabola here. So this is my velocity function. And I'm interested in, where is velocity positive? Where is this graph above the x-axis? Well, if I were to just look at it for face value, the graph's above the x-axis over here and over here. But I need to think about the context. So we're talking about time here. And we only consider when time is greater than or equal to 0. So we're only interested in the interval from 3 to infinity. So when is the particle moving in the positive direction? Anytime my t values are greater than 3. So I'm going to go ahead and say when t is on the interval from open 3 to infinity. For part E, we're asked to find the total distance traveled during the first 8 seconds. So that's asking us to find the distance traveled from time 0 to time 8, and then draw a diagram to illustrate the motion. So since we're talking about distance, we're going to need to use the position function. So let's figure out where we were at time 0. So let's go ahead and compute s of 0. So s of 0, well, that's actually pretty straightforward. If I plug a 0 into each of these t's, then we're just going to have 30 feet as our answer. So that means that the object is currently at a location of 30 feet at time 0. So I'm going to go ahead and start to draw myself a diagram over here. So I'm going to go ahead and label for myself 30, and this is in feet, and we know that this is where our particle starts. But now the question is, well, what happens in between 0 and 8 seconds? So I can figure out where the particle is at 8 seconds, so let's go ahead and do that, but I'm going to leave a gap. So if I substitute in 8 to this particular function, and I'm going to spare us all the arithmetic here, that would give us 302 feet. So way over here, I'm going to go ahead and label 302. So this is where the particle ends up at time 8. This is where the particle starts at time 0. But remember that distance covers the entire path. So I need to make sure that there was no stopping in between, because that might change things. But we do know that the object stopped between 0 and 8 seconds. From part C, we know that the object was at rest at 3 seconds. So we're going to also have to figure out what's going on at S of 3. So at S of 3, it turns out that the object is at negative 10.5 feet. So that's substituting 3 into each of these t's. So at time 0, I'm at 30 feet, and then at time 3, I'm actually over here at negative 10.5. So I travel to the left at t equals 3 seconds. I'm stopped before I turn around and head to where I'm at time 8 at 302 feet. So that was one way of thinking about what's happening by drawing out the diagram. And we still haven't computed the distance yet, but the other piece that we could have analyzed was our velocity graph that we drew a little bit earlier. So I'm just going to go ahead and re-sketch part of it. So my velocity graph looked something like this when time was greater than 0. So this was 3 over here. This is time. So this was my v of t graph. So what I know is that from 0 to 3, and over here would be 8, obviously not to scale, but between 0 and 3, my velocity graph was negative. So that tells me that I had to travel to the left. And then beyond 3, we know that velocity is positive, so that means I'm traveling to the right. So it's another way to graph or illustrate the motion of the particle on a diagram, and to realize that we have to also take into account this time or this distance, this location at time 3. So now let's actually find the total distance traveled. Here's what we have to do. So we have to figure out, well, how far did we travel between time 0 and time 3? So that's computing what's S of 3 minus S of 0. And then we're going to go ahead and have to add that to the distance traveled between time 3 and time 8. So that's going to give me S of 8 minus S of 3. So here, if I go ahead and compute S of 3 minus S of 0, then I have negative 10.5 minus 30, which, as you notice, gives us a negative number. It gives us negative 40.5. So what we have to do is take the absolute value of these quantities. So I have to take the absolute value, because I want a distance. That's got to be positive. So this distance here is positive 40.5, plus now I'm subtracting 302 minus negative 10.5. So that's going to give us positive 312.5. And we're going to go ahead and add these two numbers together, 342.5 feet as my total distance traveled. In part F, we want to find the acceleration at time t and after 2 seconds. So we already had the velocity function. We'll go ahead and take its derivative to find acceleration at time t. So a of t is v prime of t. By the power rule is 6t minus 3. And the units there would be feet per second squared. And then we substitute in 2, so the acceleration after 2 seconds is just 6 times 2 minus 3, or 9 feet per second squared. And part G, find the average acceleration over the first 2 seconds. So over the first 2 seconds means we're talking about the time interval from 0 to 2 seconds. And average acceleration is the change in velocity over the change in time. So it's going to be v of 2 minus v of 0 over 2 minus 0. So here we're going to go ahead and substitute in 2 into my velocity function. So to save us some time, that number is negative 12 minus, if I substitute in 0, I can see that the t's will become 0 and I'll have negative 18 left. So minus negative 18 all over 2. So here, if I change this to a plus, I'm going to get 6 over 2, so I'm going to get positive 3. And my units are, again, feet per second squared, because it's an average acceleration. And sometimes students get confused and they think, oh, average acceleration is a of 2 minus a of 0 over 2 minus 0. But that wouldn't give us the correct units. So we can see here that we do get the correct units, because if I subtract the two velocities on the top here, these velocities are in feet per second. And then 2 minus 0, those are times, so that's over seconds. So that's how we end up with the correct units for acceleration, feet per second squared. In part H, we want to answer when is the particle speeding up and when is it slowing down. So a particle would be speeding up if v of t and a of t have the same sign. And then it's slowing down when v of t and a of t have opposite signs. So we need to figure out where is velocity positive and where is velocity negative, and then where is acceleration positive and where is acceleration negative. So first let's go ahead and do a graphical approach, because we already started this process. So if I want to go ahead and analyze the graph of v of t, so I already had a rough sketch of it. We're only concerned with times greater than 0. So again, just a rough sketch of that velocity function was time was greater than 0. We had an intercept at positive 3. So we knew that our velocity function was negative between 0 and 3. So the velocity function was negative between 0 and 3 below the x-axis. And then our velocity function is positive when I'm greater than 3. Then I'm above the x-axis on the velocity function. And now we're going to go ahead and think about the acceleration function. So that's 6t minus 3. So that's a linear function. So if I go ahead and sketch 6t minus 3, the y-intercept is going to be negative 3. And it's a linear function with a slope of 6. So I would go up 6, right 1, so that would take me to positive 3, and then over to 1. So here I'm going to go ahead and sketch my acceleration function. I should be careful, I only want time greater than 0. So here is my function a of t. And it does have an intercept at positive 1/2. So at positive 1/2 is when my acceleration is 0, and then I can see acceleration is below the x-axis from 0 to 1/2, and above the x-axis from 1/2 onward. So I'm going to go ahead and summarize that on a little line graph for a second. So I'm concerned with what's going on beyond 0. So these are my times, and the numbers that are important on the t-axis here are going to be positive 1/2 and 3. Positive 1/2 and 3. So what I'll go ahead and do is think about the two different functions that we have here. So we have v of t and we have a of t. So v of t, what I'm going to do is I'm going to go ahead and label, well, velocity is negative between 0 and 3. So what I'm going to do is just put a bunch of little negative symbols here between 0 and 3, and then past 3, my velocity function is positive. Then I'm going to go ahead and do the same thing for acceleration. So I have a of t, and a of t is negative between 0 and 1/2, so I have negative signs here. And then beyond 1/2, acceleration is positive. So when I attempt to describe when is the particle speeding up and when is it slowing down, my particle is speeding up when velocity and acceleration have the same sign. So I can clearly see that happens. So both velocity and acceleration are negative between 0 and 1/2. So the interval from 0 to 1/2. And also the interval of time from 3 to infinity. So velocity and acceleration are both positive from 3 to infinity. And I'm slowing down when acceleration and velocity have opposite signs, which is in between 1/2 and 3. This was a graphical way of understanding a particle speeding up or slowing down, analyzing the graphs of velocity and acceleration. We also could have taken an algebraic approach to figure out where is v of t greater than 0, where is a of t greater than 0. So let's go ahead and take a look at a of t first. Acceleration was a linear function. 6t minus 3 greater than 0 can be solved by adding the 3 to the other side and dividing by 6. So we have 6t is greater than 3, or t is greater than 1/2. So acceleration is greater than 0 or positive when time is greater than 1/2, which does match our graphical interpretation. When time was greater than 1/2, acceleration was positive, and when time was less than 1/2, or between 0 and 1/2, acceleration was negative. If I were to try to solve where velocity is greater than 0 in algebraic fashion, I am stuck doing some factoring or solving for where the quadratic equals 0 to find its zeros. So here, from previous work, we know the zeros end up being -2 and +3, but we're only actually concerned with +3 because we're going to create ourselves a sign chart that starts at 0. So we have 0, we're going to label 3, all the way to infinity is what we're concerned with. So we're doing a sign chart for v of t. And what we have to do is pick a test point between 0 and 3. So we can go ahead and pick the value of 1. And between 3 and infinity, we can go ahead and pick the test point 4. And those test point values, I'm going to plug 1 into the t here into the factored version. I can see that I'd end up with 1 plus 2 is positive, 1 minus 3 is negative, so overall multiplying these, I would be negative on that interval. So that test point represents what's happening over that interval. And if I substitute in 4, I end up with a positive times a positive. So on the interval beyond 3, I have velocity as positive, which again matches what we did in the graphical approach. So between 0 and 3, we had velocity was negative. And then from 3 onward, we had that velocity was positive. Let's look at a different type of rate of change example. The amount of coffee in a pot in ounces is modeled by b of t is equal to 16 minus 16 e to the negative 0.4 t, where t is in minutes after the start of brewing. Using this model, find b prime of 5 and explain its meaning in the context of the problem. Alright, so let's go ahead and take a closer look at this function. B of t, 16 minus 16e to the negative 0.4 t. I have an exponential decay function here since the growth rate is negative. And this models the amount of coffee in ounces after t minutes of brewing. So the output units here would be in ounces. So if we plug in 5 into b of t, that would give us an amount of ounces. So at 5 minutes, so many ounces were in the pot. Now, what we're asked to do is, using this model that's given, find b prime of 5. So find the derivative and then plug in 5 and explain what that means. So first, let's go ahead and take the derivative of this function. It's going to require a chain rule. So we have b prime of t is equal to, the derivative of 16 is 0. Here, this is going to be a chain rule. So the derivative of an exponential function is just the exponential function. So it's like we'd have negative 16e to the negative 0.4t, but then we have to take the derivative of the inside. And the derivative of negative 0.4t is just the coefficient in front, negative 0.4. So then this is times negative 0.4. That's the derivative of the inside. And so when we multiply the negative 16 and negative 0.4, we get a positive 6.4 e to the negative 0.4t. That's b prime of t. Now we're asked to find b prime of 5, which is simply plugging 5 into the t. So b prime of 5 is 6.4 e to the negative 0.4 times 5. And if we use a calculator to approximate this, we get approximately 0.866. But now the question is 0.866 what? What did we find? When we found b prime of 5, we found a numerical quantity, but it means something in the context of the problem. So explain its meaning. All right, so b of t gave us an amount, a quantity in ounces. When we take a derivative, that is a rate of change. So here, the rate of change, the units of the rate of change would be ounces per minute. So we have 0.866 ounces per minute. So that's the units of b prime of 5, but that is still not enough. That's not an explanation. So what we'd want to do is we'd want to say something like, at t equals 5 minutes, the rate of change of coffee is 0.866 ounces per minute. Or we can actually say a little bit more, or something that's a little bit more descriptive. So we can say something like, at t equals 5 minutes, the amount of coffee is increasing by 0.866 ounces per minute. And we know that the amount of coffee is increasing because the rate of change, because b prime of 5 was greater than 0. So that slope of the tangent line would be positive, right? Would be positive. So we would know that we have the amount itself would be increasing. So there's different ways. It doesn't have to be the exact same way to explain the meaning, but we have to somehow involve the notion of the rate of change of coffee, right, in ounces per minute, or the idea of saying the amount is increasing is talking about that change, because that change, the amount being increasing, we're discussing the change in that quantity, just using a different word, using increasing. And then by the specific amount. We also want to make sure we say the specific time. So this is this number 0.866 is specific to the 5-minute mark when we're keeping track of what's going on with this coffee. Before moving on to the next example, we're going to go ahead and fill in some blanks here. Let's look at some terminology in rates of change. So when we see the word initial or initially, it means that time is equal to 0. So time is equal to 0 if we're talking about initial or initially. If we're talking about at the origin, that means that position equals 0. And the position function might be s of t or x of t. Whoops. And so that would be set equal to 0. When something is at rest, that means that velocity is equal to 0. And velocity is v of t, so we would be setting v of t equal to 0. When we see the phrase, the maximum height of a ball being thrown into the air. So if we're thinking about throwing a ball up into the air, that's going to occur when the velocity is equal to 0. So if you think about throwing a ball into the air, right when it reaches its very, very top height, it stops for a second. So v of t equal to 0 is meaning velocity stops. It's at rest just for that second before it starts traveling back down again. If we see the phrase, if an object is dropped, so if we drop an object, what does that tell us? It tells us that its initial velocity, so at the start, the object is dropped, so its initial velocity is 0. If we drop something, its initial velocity must have been 0. It was just dropped. It wasn't thrown, right? Then it would have an initial velocity. But if we just let it go, its initial velocity is 0. So v of 0 is equal to 0. When an object in vertical motion hits the ground, so think of that ball again. So we throw a ball up into the air. When it hits the ground, its height, or basically its position, is equal to 0. Its height is equal to 0. So if an object hits the ground, then its height is 0, right? It's right on top of the ground. There's no space there. The height from the ground would be 0. But a lot of people think it's velocity, but that's not the case. So when an object is in vertical motion and it hits the ground, its height is 0, not its velocity. So I think what's happening is people think, well, it's on the ground, so its speed is 0. But we're talking about the moment it hits the ground. Right when it hits the ground, its velocity couldn't be 0. Think about dropping an egg from the top of a building. When it hits the ground, if its velocity was 0, then it wouldn't break when it hits the ground. But it hits the ground with a force, right? So that's its acting velocity. So the only thing that's 0 when an object hits the ground is its height, not its velocity. And then these last few questions are going to seem like common sense, and they are, but I just really want to make sure I discuss them. If the question asks you when, or at what time, or how long, your answer needs to be a time. So seconds, minutes, hours, right? Those are the units of times. As opposed to if you're asked to find a speed, a velocity, if you're asked how fast, what is the rate, or for a rate of change, then your answer needs to be a rate. Which again might be obvious, but sometimes when I'm reading solutions, the question will say, when did the ball hit the ground? And someone will say 5 meters or 5 meters per second. And that doesn't make sense. When implies a time, right? It happens at 10 seconds. But it doesn't make sense to have the answer to a when question to be 5 meters per second. And then remember, you are being given a rate whenever you see words like per or for or in, right? Like miles per hour, 10 books in one day. So this is just all just important terminology that you can refer back to if you get confused on what exactly you're supposed to be plugging in or setting equal to 0. In this example, we have the height in meters of a projectile shot vertically upward from ground level with height given by h of t equals 80t minus 16t squared after t seconds. In part A, we want to find the initial velocity and the velocity after 2 seconds. So let's start with that. The initial velocity means the velocity at time 0, because again, initial means time 0. So we need to go ahead and take the derivative of this function, because this is essentially a position function. It tells us the height to get to velocity. So we have, we're finding h prime of t, that's v of t, is 80 minus 32t by the power rule. And then we're going to plug in 0 to find the initial velocity. So v of 0 is 80 minus 32 times 0. So we get 80, with units being meters per second. So the height was in meters. That was the units of h of t. When we took the derivative, it became a rate. So we have meters per the unit of time involved, which is seconds. So this is my initial velocity. And then I want the velocity after 2 seconds, which means I want v of 2. So that's 80 minus 32 times 2, or 80 minus 64, which is 16 meters per second. So we have our initial velocity and our velocity after 2 seconds. Now the second part says set up but do not evaluate the expression needed to find the average velocity of the ball during the first 2 seconds. So we want to find the average velocity on the interval from 0 to 2 seconds. And the setup to find average velocity is going to look like a quotient. So we're going to have the change in position over the change in time from 0 to 2 seconds. So the setup is going to look like h of 2 minus h of 0 over 2 minus 0. So this is going to be the setup here, and I want to go ahead and attach units to it for a second so that I can really verify that it is a velocity. So when we subtract two heights, the units are going to remain a height, and the units of the height were in meters. So in the numerator, our units would be meters, and in the denominator, 2 minus 0 is seconds, so we do have a velocity. We have meters per second. I can tell you the most common mistake on this problem is when people see to find the average velocity, they do v of 2 minus v of 0 over 2 minus 0. But let's talk about why that would be incorrect. Velocity would have units in the numerator of meters per second, and then 2 minus 0 is in seconds. So that would give us meters per second squared. So that is not giving us average velocity. This is giving us average acceleration. So we really have to be careful, right? This would be average acceleration on the interval from 0 to 2, which is not what we're being asked for. So when we find average velocity, it's the change in distance over the change in time. So it's not this one, right? This is my setup, and it was setup only. We didn't actually evaluate it by plugging into h and plugging in 0 and solving all the way. In part B of this question, when does the projectile reach its maximum height? What is the maximum height? So when an object was in vertical motion, it reaches its maximum height when the velocity is equal to 0, because just for a second at its maximum height, it's at rest. So what we need to do is set the velocity function equal to 0. And we found that the velocity function was 80 minus 32t. So we're setting that equal to 0. So let me add that extra detail up here. We're setting v of t equal to 0. And so we end up with 80 equals 32t. If I divide by 32, I get t equals 2.5. And the units there, since it's a time, would be seconds. So this answers the first part of the question. When? When does the projectile reach its maximum height? Well, that time is at 2.5 seconds. The second part of the question is, well, what is the maximum height? Well, if I know it happens at 2.5 seconds, then I simply plug 2.5 into the h function to find that maximum height. So we're going to do h of 2.5. So we have 80 times 2.5 minus 16 times 2.5 squared. And we actually get a nice number out of this. We get exactly 100. So that height would be 100 meters. In part C of this problem, we're asked, when does it hit the ground? So the projectile, when does it hit the ground? And the second part of this question is, with what velocity does it hit the ground? Well, when an object hits the ground, remember, its height is 0. Its height is 0 if it's on the ground. So when we think about being on the ground, we need h of t to equal 0. Well, here's my h of t function. So we're setting 80t minus 16t squared equal to 0. To solve this quadratic equation, I'm going to factor. I'm going to factor out a 16t, and I'm left with 5 minus t, in parentheses, is equal to 0. And then I can set each factor equal to 0. So 16t would give me t is equal to 0. And then t is equal to 5. All right, so these are both times, right? So time, this is 0 seconds and 5 seconds. We want to be careful about something, though. This question says, when does it hit the ground? So remember, this is a projectile that was shot vertically upward. And so it's going to go up, and then it's going to hit the ground at 5 seconds only. So at 0 seconds is when it was launched. That's not when it hit the ground. So we want to pay special attention to hit the ground, which means the answer is only 5 seconds. At t equals 5 seconds is when the object hits the ground. Now the second question, with what velocity does it hit the ground? So we said, the velocity isn't 0 when it hits the ground. That doesn't make sense. It's got to hit the ground with some force. Well, if it hits the ground at 5 seconds, the second part of this question is answered by plugging 5 into our velocity function. And that was 80 minus 32t. And so we're going to plug in 5 into t. So we get negative 80 meters per second. Negative 80 meters per second. So that's the velocity that it was traveling. Now, what does that negative mean? So this negative means that the direction, it indicates the direction of the object. So because it's negative, right, the ball is falling down. Right, so the velocity is all about the direction. So if it's positive, it's moving to the right or left. Or I'm sorry, if it's positive, it's moving to the right or up. If the velocity is negative, it's moving left or down. Since we're talking about an object in vertical motion, negative would imply that the object is falling down. In the last part of this problem, we're asked, what is the velocity of the ball when it is 96 feet above the ground on its way up and on its way down? What is the velocity of the ball when it's 96 feet above the ground on its way up and on its way down? I'm going to go ahead and sketch a little picture of the height function of the ball for a second. So we know that the ball starts, so here's my h of t, here's t in seconds. The ball starts out at the origin, and then it's launched upward and it falls back down, right? So it's going to have this parabolic shape, right? I have a parabola, and I know that it hits the ground at 5 seconds, so I can label that right here. The maximum height of the ball occurs at 2.5 seconds, and it happens to have a maximum height of 100. We found that in a previous part. Right now, what we're being asked is, what is the velocity when the ball is 96 feet above the ground? Now, let's say this is 96 right here. So the ball is 96 feet twice, once on its way up towards its maximum height, and then it crosses 96 feet high again as it's on its way down. But I want to know what's the velocity of the ball at that time. So that's asking for the slope of the tangent line, right? What is the slope when the ball is exactly 96 feet above the ground? Well, first, I'm going to need to know when that happens. When is the ball 96 feet above the ground? So I'm going to have to set the height function equal to 96 to find those times when it happens. Whoops. Right, so I'm in search of what time, right, question mark, what time it happens. All right, so we're going to set 96 equal to 80t minus 16t squared. So what I can go ahead and do is divide out the 16. So each of these is actually divisible by 16, and we're going to get a lot nicer numbers. We're going to get 6 is equal to 5t minus t squared. It's a quadratic equation. I'm going to set it equal to 0. So I'm going to add the t squared to the left, subtract the 5t, leave the plus 6, set it equal to 0. We want quadratic equations equal to 0. This is best case scenario because this thing factors to t minus 3, t minus 2. So we get t equals 2 and 3 seconds as those missing times. So at 2 seconds on its way up, at 3 seconds on its way down is when the ball is 96 feet high. But I want to know the velocity at those times. So I want to know what's v of 2 and what's v of 3. Well, v of 2 we actually found in part A of the problem. So v of 2 was 16 meters per second. So that's the slope of the tangent line here. If I plug in 3, so it's 80 minus 32 times 3, I actually get negative 16 meters per second. And that should make sense given our rough sketch because of the symmetry in a parabola. If this slope is positive 16, then on the exact opposite side, it's going to have to be the same slope but negative. So on its way up, I have a slope of 16 meters per second, so I'll just put a little up here. And then on its way down, it has I should be more specific, it has a velocity of 16 meters per second. On its way down, it has a velocity of negative 16 meters per second.